so we have two bottles here. We have a thin bottle and a wider bottle. This would be a big capacitor, that would be a small capacitor. Now, the height of the water is like voltage. If you imagine you're at the bottom of this, or would we all agree that if I were to take a water bottle that has a hole in it, so as that water comes out, notice how far it goes, but then as it gets lower and lower and lower, the speed of the water is going to decrease. Or the current will decrease because there's less height or less pressure or less voltage. So height equals voltage, okay? Now over here, these have the same voltage, but the bigger capacitor has the most water, which would be the most charge. If they had the same charge, they would have the same amount of water. And for the same amount of water, this one obviously will have the lower voltage for the same amount of water. All right? So if they're in parallel, they have the same voltage. Which one will have more charge? The bigger capacitor. If they're in series, they have the same charge. So therefore, which one will have the most voltage? The smaller capacitor. So with that knowledge, just as when we did on a battery, and we said, or if we say that this is the EMF, that's getting hard to read. So we have a battery here with an EMF, and we have two resistors. We know that each one, if they're equal resistors, they'll have equal voltages, right? Mm-hmm. But the bigger one will have, the bigger resistor will have more voltage. Do we all agree with that? Mm-hmm. So if this were 2R and R, this one has more voltage. Yes? However, if we did this, is that supposed to be equal? Let's say that this is C2 is greater than C1. Because they're in series, they have the same current. So they'll have the same amount of water. But the smaller capacitor, if they have the same water, will have the highest water level, which means V1 is greater than V2. And it will be proportional. In other words, if this is half the size, it will have twice the voltage. If we put them in parallel, you good? So now they're in parallel, therefore they have the same voltage, which on the water bottles is the same height of water, but the bigger one will have more charge because it has bigger plates. So in this case, they both have EMF. This one will have 2Q, and that will have 1Q.
And what's the logic behind that again? Like why it has more charge?
It's bigger. It has bigger plates, so it can spread out. Because remember, as you're putting charges onto a plate, well, pretty soon they're being pushed by the battery. Well, pretty soon they're resisting each other, and now they start to push back against the battery.
So if you have more.
And that's the back voltage. Yeah. In more area, they can spread out more.
So you have more back.
Yeah.
Okay.
Okay, we all good on this, yes? Okay. Next thing we should hopefully remember. We remember that resistors and capacitors work opposite, don't they?
Yes.
So if this is C and this is C, then C total equals
1 over C plus 1 over C.
C over 2.
Oh, yeah.
If they're equal capacitance.
Yeah.
If they're not equal, then 1 over C equivalent, or C total, 1 over C1 plus 1 over C2. If they're in parallel, if they were equal, the total capacitance would equal
2C.
2C, but we know that the total capacitance now equals C1 plus C2. Are we all good? And if you have a series of capacitors, then you do them as redraws, right? Just put them together. Like for instance, if I were to do this, if these are all the same, then this right here, the total would be
C over 2.
2C, because they're in parallel.
Oh, shoot, I did
This
backwards.
would be C over 2.
Yeah.
So it'd be 1 over C over 2 plus 1 over 2C equals the equivalent.
Yeah.
This is the parallel. This is the series. But because these two groups are in series, you have to do that. We all good?
It's real crazy.
Okay. Next thing. If we have a capacitor, let's go back to our very basics. A capacitor, C equals Q over V. Which one of those is a constant? C. Given the same capacitor, in order to change the capacitance, you'd have to do what? Change it something, physically change its area, etc. So let's talk about how we could do that, okay? So let's say that we have a parallel plate capacitor. We'll call that D. We'll call that 2D. If this one is C, then this one is C over 2. Because you've doubled the distance.
Yes.
That's why capacitors in series are less total capacitance, because you've increased the distance,
Oh, okay. Oh, actually.
right? You could actually look at this and say, oh look, it's two capacitors in series, 1 and 2. What if this is A, this is also A, but that's 2D. Then we'll go to this one. This is A over 2 times D. The capacitance would be C over 2. If I do this, then the capacitance equals 2C. If I half the distance, it's twice the capacitance. Why is that physically again? Because when you're putting charges on the capacitor plates, the closer they get, they start to be attracted across the gap. And then you can put more current, you can put more voltage. The voltage can push more. You can put more charges on. When you increase the plates, it's like we talked about, they spread out more. Okay? We all feeling pretty good about that? Yes?
Uh-huh.
All right. So now let's do something weird.
Yeah.
Let's talk about kappa.
Cap?
Kappa. Oh no, before we do that, we're with kappa, let's look at this a little bit. So if we have a capacitor, I'm just going to have the plates, I don't need to connect it. So let's say that these are the positives, these are the negatives, and electric fields go from
Negative
positive to negatives.
You gotta go.
Okay, we're all good with that, yes? If I did this, would it be the same electric field? You see how the density of the lines is the same?
Oh, yeah.
So, Q is proportional, sorry, that would be the wrong way of doing it. E is proportional to Q. If I were to reduce the number of Q's, wouldn't the number of lines decrease?
C.
So as Q increases, E increases. That makes sense, yes?
That's
Yes.
only if it's a flat plate though, right?
Well, if we look right there, you can see E equals KQ over R squared. It's proportional to Q also.
Okay.
And we did this only one day where we talked about Gauss's law, where we had an infinite plane and we put charges on it. We said it had a density of sigma. And we found out that the electric field on an infinite plane equaled sigma over 2 epsilon naught. And what is sigma? How many charges are crammed onto that plate. So the electric field is proportional to the density of the charges. So if you have a capacitor and you're charging the capacitor, guess what's happening to the electric field? It's increasing. isn't V also increasing as you're charged? Well, wow, I hadn't even thought about that last period. Well, let's do this. We have a charging capacitor, right? We know our equation, V equals epsilon, or the EMF times 1 minus e to the minus t over RC. Yes? So this is going to increase over time. So we have a charging capacitor. This is going to be V versus T. Well, if C is a constant, then Q equals CV. As V increases, C increases. And since E equals volts per meter, if D is constant, V increases, E increases.
Only if it's
So let's write these equations we have. These, we're going to write E equals V over D. We good?
Did you say C wouldn't change that?
What's that?
Did you say C was a constant?
C is a constant unless you change the plates,
Aren't you just,
like we just did here.
aren't you just increasing the voltage though?
Well, let's look at that. If Q stays constant, E stays constant, right? So looks up here. E stays constant. D increases. V must increase. This might be easier if we wrote V equals ED. Constant goes up, goes up, goes up. So let's write some rules here. So we found out that as Q increases, E increases, right? Remember that?
Yeah.
Okay. We've also found out that as D increases, C decreases and vice versa. Yes?
Yeah.
What about if we take, if we're connected to a battery? If we're always connected to a battery, what do we know?
EMF is constant.
V is constant. Now, is that helpful, or is it better to put delta V equals 0? Is that better?
V equals constant, yeah, that's
Okay.
right.
If not connected to a battery, what's true? Q
Delta Q.
equals constant.
Ooh.
Right, because they're trapped on the plates.
Yeah.
Mhm.
Yeah.
We all feeling good about this?
Mm-hmm.
All right, now it's time for us to do here. In this case, what's true? Connected or not connected?
Not connected.
This is
A charge
not
capacitor.
connected to a battery. So, what happened? Delta Q equals 0, yes? So what else equals 0?
Delta E.
What did we just say? Q is constant, E is constant. Yes?
Mm-hmm.
What else? So we look at our equation. What happened to C? Oh, so D went up. So
C went down.
C went down.
C went down. And we look at this equation here. Q is constant. C went up. No, C went down. V goes up. Another conceptual way to think about this. I take a small charge here. I take a positive charge, I release it. It speeds up. And it has a distance of d to speed up. Over here, I have a positive charge. Doesn't it have farther to speed up? And since voltage equals joules per coulomb, this region has more joules of potential energy. Therefore, it has more voltage.
Mm.
Now how about over here? We'll say not connected. No, that's not connected, this is connected. Okay, so in this case, we have Then we pull it apart. This equals V. It's really delta V, right? You understand that's delta V, it's the difference of voltage?
Yeah.
Okay, and over here? It's the same V, right? Because they're connected to the battery.
Right.
So, D went up, C went down, V is constant. Q equals C times V. C went down,
And
constant,
so Q went down.
went down,
So Q goes down.
Q goes down. They went back to the battery.
The charges.
Oh, it's the back voltage increase.
Because we went like this, they're not attracted
You can't
across the
pump that
gap
many, yeah.
anymore, so they pushed back into the battery.
If the voltage is constant.
So could you?
Well, and if Q went down,
E goes down.
E went down. I think we just got something, didn't we? This is way better than what I did last hour. So once again, Q is directly proportional to E. As the amount of Q goes up, the electric field goes up. That makes sense, right?
Yes. Yes.
Right? If D goes up, C goes down. If you're connected to the battery, what's true? If it's connected to the battery,
Oh,
V is constant. If it's not connected to the battery, Q is constant. Are we all good?
Yeah.
And then look at our logic again here. You separate them. Q stayed constant. E stayed constant. D went up. So, right here. E is constant. D went up. V went up. And C went down. Over here. Over here. V is constant. Look here. V is constant. D went up.
E goes down.
E goes down. And if E goes down, Q goes down. Or
B goes up.
V is constant.
R V is constant. And then
Yeah, if we take this and we put them together, I feel stupid I didn't think of this earlier. So if we take this and we plug it over here, we get
C equals Q over ED.
Q
C over Q equals ED.
over ED,
Yeah.
which says that ED equals Q. I can't believe I've never seen that before. So now we know for a fact that Q is proportional to E.
C. It is E fact.
Yeah.
You like erase the C.
Yeah.
It's E. That.
Sorry. Q,
C equals
Q equals C ED? Yes?
Yeah.
Q equals SED.
And then you can like,
That's an important thing.
then you can also put in the physical definition of a capacitor, and there eliminate the D.
Oh, yeah, thank you.
Equals what?
Q equals epsilon naught, A over D. Oh, yeah, look at that, nice. Q equals epsilon naught,
Yeah.
A times the electric field. The electric field is directly proportional to Q. You increase Q, you increase E. Thank you, Luca. I knew there was something in there I was looking for in that, instead of using two equations. Now we have the equation. How we feel about that? Pretty good?
Perfect.
So now we can say that Q is directly proportional to E. Just like before, remember when we were doing the LC circuits, we said that when we go from the charge, then we take dQ dt. Remember we were kind of following the different things, right? You've got to know which one goes to where. So really we have two equations. This one and this one. This one just comes from the definition of electric field, right?
Yeah.
Volts per meter. And that's the basic charge, basic capacitor equation. How we feeling about that? Better?
Good.
A lot better.
Thank you, Luca. All right, let's go on to the next
Wait,
step.
wait, 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 wait.
He's gonna take a
It's a
picture.
video, right?
Yeah, they have a video.
We're good, we're good. We got a video.
I'll just write it and you can get the picture and we go on, okay?
AE.
You know what
And
sounds
then
cooler?
a D at the bottom.
Nope, D cancels.
No.
Oh, right there.
Yeah, that's what.
You gotta like,
Thank you.
It hasn't fixed it yet. But yeah.
Go, 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 go.
Get a picture if you want to get the picture now.
it just feels
We
better.
good? Okay. Go ahead and pause while I'm doing this. That's in the, I don't think this is on the test, but I might as well just point it out. If you had a capacitor and you charge it to a particular voltage and to a particular Q,
Mm-hmm.
okay? And you know that you could find that from C, right?
Yeah.
So that Q equals CV, yes?
See.
All right. Then we take this, we disconnect it, because it's now charged, right? We connect it then to another capacitor.
Oh.
Those capacitors are now in
Parallel.
But the total charge of Q is the only charge available.
So they have this.
Let's imagine this is C and this is C and they're the same capacitors. Half of it will move to the other side.
Right.
Pretty cool.
Yeah,
Right?
it splits, right?
Because they have to be the same voltage, don't they, because they're connected to the wires. So this will move over there, this will move over there. Now, if they're different capacitors,
Like one's 2C.
remember, what is, for the bottles, what does Q represent?
No height, charge.
Oh, water.
The water is the amount of charge. If you connect two water bottles, and they
Oh,
have the
wow.
same amount of charge,
And height.
Wait,
no,
is it-
no, they're connected, there's one,
which
there's
one's
a
voltage
certain
again?
amount of water,
Height
right,
or
in
depth?
one. You connect them, won't they go to the same
Oh, okay.
height?
So they'll always balance out.
They'll balance out, they'll go to the same voltage, the same height, and the smaller one will have less charge.
What does width represent again?
That's like
That's
a
capacitance.
bigger capacitor versus a smaller capacitor.
Wait,
Got it.
if you had two different shaped water bottles that go to the same height,
Yeah.
what if you had like a really long narrow bottle and then just like a really fat bottle?
Same height.
It would
Same
still be
height,
the same.
yeah.
But then the bigger one
We'll have more.
will have more charge, not the smaller
It's
one.
like a basing.
The one with more area would have more.
Oh, yeah, the one with more area.
Okay, Louis, pause. Okay, now, if you'll notice where his water is and where, once it cools, once it calms down, you see that the two levels are equal.
That's pretty crazy.
Now, just by the way, when I was in, when I go up like this,
What?
They balance out still.
they balance out.
Yeah, it bounces back and forth.
Yeah, because it's just like a wave,
Yeah,
right?
it's fluctuating.
Now, when I was in Mexico one time doing some volunteer work, and they were building a church or something, and they don't have laser levels or all that kind of stuff. So what they did is they took a long tube, and they take it down there, and they take it over here. And as long as there's no air in the tube, they would just go like this on one side, go that on the other side. They're level. Notice that's wide, and this is thin, and yet they're at the same height. So likewise, when you put things in parallel, they go to the same height. Why is that? Because it turns out that water pressure, this is something Mr. Mark and I have been trying to figure out how to show. This kind of shows it a little bit.
Yeah, that's actually pretty
But
good.
that
Like-
it only depends on height.
Regardless.
It doesn't depend on width. Pause.
So-
I guess you. Whoa! Don't record yet.
Oh wait, he's drawing. Never mind.
Can you believe
I can't actually.
You ready?
It's already going.
Okay, so once again, as we just saw in the back, right here, when you put this capacitor in with that capacitor, their heights, because they're in parallel, the heights will equalize. So the bigger capacitor, the wider capacitor will have equal heights, so the bigger capacitor will have more water or more charge. There's a lot of these I think you can solve with the water idea, okay? Over here, just by the way, while I was thinking about this, when you're pushing positive charge this direction, and the negative charges are moving this way. This side becomes negative, this side becomes positive. Well, you see that these are isolated? They
Yeah,
can't
they're-
get through there. So where does this charge come from? Right there. So this charge goes there. And once one of them is full, which would be the smaller capacitor, the big one stops too.
Yeah.
Okay?
That's why it has more voltage state charge.
So let's remind ourselves what we did a little bit ago, just so that we can do this easier. Charging capacitors, we can do that real fast as well. So if we had the equations that you have on your worksheet, but for instance, we have V equals epsilon 1 minus E minus T over RC. We know that RC is the time constant, and that's the amount of time for it to go within 37% of its final value. If it's, in this case, it's charging, so it's going to go up within 37% of total, which is that, EMF. And then it's going to go up within 37% of 37% of the total, then 37% of 37% of 37% of the total. If it's discharging, which would be, this is the initial voltage, which in this case would be EMF, but it doesn't have to be. So in this case, it would drop to 37% of what's left, then 37% of what's left, then 37%. Which wouldn't it be this? Let's say that after 1 RC, you get this, right? This would be e to the, yes? Well then, let's put that in here. This voltage would be, right? That's what's left, yes?
Mhm.
This becomes the new initial voltage, becomes the new initial voltage, becomes the new initial voltage. And since this is 37%, then this would be 37% of 37%. This would be, this is 37%, which is this.
Because it drops to 37%.
It drops to 37% of what's left
Total.
every RC.
Right. So you get a new total and then it goes.
Yep.
okay.
Now, you don't have to do that, but you can just keep putting in 1 RC, 2 RC, 3 RC, 4 RC. Now, solving these equations, just to make sure we know how to solve them. So, in this one, so we get V equals EMF e to the minus T over RC. If, I'm going to try to get to that. So we're going to switch them, and we get EMF e to the minus T over RC equals EMF minus V at some time T. Divide by the E, of our epsilon, or sorry, EMF. Then,
Natural electric.
and the rest of it's just, just math. Because once you have that, then you just solve for whatever you're looking for, right?
Yeah.
Now, looking at this, if you get to this point, unless they ask you for an expression with just letters, I would probably calculate that. And for this other one that we had over here, so like I equals I naught, I should be able to do this and not blink an eye on this. That's one iteration. You shouldn't have to go through the individual steps. Yes?
Yeah.
And since I naught is bigger than I, this is a negative number. That gets rid of that negative, blah, blah, blah. That's how you deal with these equations. Now for capacitors, we're charging a capacitor. To make this even easier, this is the EMF total, what if there were 2 batteries there. Then this is our total, and this would be C total. Now, how would I find I naught? Well, at the beginning, in the steady state, a capacitor at the beginning is like a wire, and at the end it's like a break. So I naught will equal EMF minus R total, or divided by R total. Yes? RQ final. Since that just equals C times V final, which will actually be EMF. And what's our V final going to equal? EMF. now we have all of our coefficients. If you look over there, these are on the worksheet. You have your charging and discharging, capacitor equations, and you would just, once you have those values, you can put them in. And then Kirchhoff's rules still matter. If this is half of V, then that would be half of V. If this is 1/4 of the total voltage, this would be 3/4 of the total voltage, etc. We follow what I'm doing there? Okay. Now, reminding us what we did a second ago with capacitors, because we'll need this. Once again, if we have a capacitor and we double, this is 2D, this is D, if this is C, this is
C over 2.
C over 2. If we go to D over 2, that would be 2C. If we go to the same width as the original one, I'm sorry, I'm going down this way like most teachers. Wow, that made it even worse, whatever. So this is D, and let's do half A. D and A over 2, that became
C over 2.
C over 2.
C over 2. Does everybody follow what I'm doing here?
Yeah, no.
It's
like
2 over A.
It's like A over 2D.
So if you half A, you get half the capacitance.
Yeah.
Oh, I thought
If
it was
you-
compared, I thought that was
Compared to
one-
this.
Having A.
I thought it was compared to the one to the left.
No, so this is A,
Distance.
A, A.
Yeah.
Do we all agree?
Yeah.
So if I half the area and I half the distance, it would be C.
Yeah.
We all good with that? Well, now what we're going to talk about is good old kappa. Kappa is the dielectric constant.
It's a funny looking thing.
It's kappa, it's not K. Now, when you're talking about this dielectric constant, this is some sort of material you put between the capacitor plates, and you get a new capacitance. Now, what happens with that? Well, if we were to take, again, a parallel plate capacitor, and we're going to put, let me make that bigger so you can see it better. We have a parallel plate capacitor, and we put a dielectric inside of it. Let's call this our positive side, and this our negative side, and we get that the electric field wants to do this. Yes? But inside, because it's because if it's a conductor, the electric field inside would be 0. If it's an insulator and it can polarize, then this would attract negatives. This is not writing very well. What color is this bright enough? Good enough. If this will polarize, right? Positives attracted to the negatives, negatives attracted to the positive, and the electric field here would go in the opposite direction. And since electric fields are vectors, even if they were scalars, it would still cancel each other out. So by putting a dielectric in, you've reduced the voltage, or sorry, you've reduced the electric field. If it's attached to a battery, right? Then if this is constant and C goes up, Q will go up by the same amount.
But if the electric field went down,
Because it's Q over ED.
C would go up.
Okay? If, how do I prove that?
So then it's C equals Q over
Um,
ED.
Yeah, okay, here's the deal. Once you put the dielectric in, E goes down, V goes down, yes?
yeah.
But it's connected to a battery. So the battery, even though the voltage in the capacitor has just gone down. So beforehand, let's say you do this. Here's your voltage, here's time. Oh, they could give you one of these. So let's say this is time equals kappa. In other words, that's where you put kappa in. So this sucker's charging. And it gets up to some point. Let's say here's your maximum, right? Well, yeah, let's just do that. Let's say it goes to the maximum. Our maximum is there. So it charges to the maximum. It's at the maximum, you put in kappa, the voltage drops. And it recharges.
Yeah, it picks back up, right, yeah.
Wouldn't it recharge higher though?
No, it's connected to the battery. It will have that same voltage.
Oh, yeah.
Yeah, it's not like it's being pushed more voltage.
But what is
after
it
drops.
doing? It's pushing more charge onto the capacitor now that you have the dielectric. Because the Qs, remember the Qs, how they were trying to push off?
So it has more charge.
It has more charge because it went back up to the same voltage again. And how does it do that? By putting more charge on the capacitor.
Because it decreases the area they have to jump, right?
No.
Nope, because the Qs are attracted to the dielectric inside.
Okay.
So it's less, they're not pushing against each other as much as they are pulling into the center.
Yeah.
So
you
what
can
if
put more
Sorry,
charge
it does
onto
the same thing as if you move D down.
Yeah.
Wouldn't the capacitance be the same then?
It actually turns out that our capacitance now, our capacitor equation actually equals this. That's our capacitor equation. When you're just talking about can you see that all right, Louis? So our normal capacitor equation, epsilon naught just equals 0. Or sorry, equals 1. So K equals 1
If it's air.
for air or a vacuum. And K is greater than 1 for a dielectric. So just like reducing D increases C, increasing kappa increases C.
So typically a dielectric must be insulator, right?
Yeah, for two reasons. One, because it can polarize, which means it can pull charges in,
Yeah.
which makes it better. And number two, it actually turns out the highest dielectric constant, which we'll keep working on next chapter as well. The highest dielectric constant, if I remember correctly, are conductors. You're like, whoa, so I should put a conductor in there. Sure, and then all it will do is conduct the electricity
And it'll
straight
be
through.
like a wire.
So the dielectric needs to have two things. One, it needs to increase the capacitance by polarizing, and number two, it needs to resist electric what's it called, arcing, electric breakdown. Okay, like when you've got a like, remember how we showed it? We had the things that got close. Yeah, you put a capacitor in there or a conductor in there, it's just going to gap it.
Exactly.
But if you put, it's going to spark.
Mm-hmm.
But if you put an insulator in there, you've guarding against sparking, and you're increasing the capacitance because you've decreased the electric field inside. I know there's a lot of steps there,
Yeah.
but this is the stuff you have to go through and convince yourself of. Okay? Now, let's figure out what happens using this stuff that we had up here. Here's how easy this actually is to add a dielectric and figure out. You can actually, as we just showed, our new equation, which I think I wrote up there, that C equals kappa epsilon naught A over D. Okay? We already know how to do capacitors in series and parallel, don't we? Right? Well, let's do this. Say we have a capacitor. This is D. This is A. Its capacitance equals C. Okay, we all good with that? Its capacitance equals C. And then we do this. We put a dielectric in half of it. Well, what's C up? Equals the top part, let's call it C1 and C2, that would be easier. So C1 equals what? Well, beforehand, what does this one equal? That equals 2C, doesn't it?
Mm-hmm.
Now look over here, we reduce it by 2 equals 2C, right?
Mm-hmm.
So this one equals 2C. Well, this one is 2C times kappa,
Which is greater.
which is even bigger. And now they're just in series. So 1 over C total
So it's just 2C.
equals 1 over 2C plus 1 over 2 kappa C So now we have to find common denominator, and that would be 2 kappa C, right? So this will be 1 plus kappa. Yes?
Yeah.
So C total equals 2 kappa C over kappa plus 1. Did I do that right?
Yes.
Well, let's look at this. If kappa was 1, this would be, let's say kappa equals 1, then C total equals 2C over 2 equals C, which is what we had before, right? But let's say kappa is greater than 1. So if this was 1, let's say 1.5. Sorry, I'm running out of space. Let's let kappa equal 1.5. Well then, C total equals 3C, 1.5 times 2 over 2.5. It's still greater than C. Any kappa greater than 1 will mean that this increases your capacitance, which we already knew. But what if I put them in parallel? Aha. There, okay. So now we have our same capacitance. This is A, this is D, and our capacitance is C. We're all good with that, right? Now I do this. Well, isn't this side will equal, let's call it C left, will equal
C over 2.
C over 2. So then this one must equal kappa C over 2. See how that's working? So now, because they're in parallel, we add them together. So our C total equals C over 2 plus kappa C over 2, which equals C over 2, kappa plus 1. So if kappa equals 1, which would be nothing there, right? Kappa equals 1 is air. Then C total equals C.
Makes sense.
Let's say kappa is 1.5. Then that would equal, and C total equals 2.5 over 2 times kappa, which is greater than the kappa we had before, or greater than the capacitance we had before. And as you're fitting this in, you're going, you move this in. It's increasing the capacitance as you move that capacitance in. As you move the dielectric in, you're increasing the total capacitance. Now let's get crazy, and let's do this.
Put it on a ramp.
On a ramp.
Yeah, the
Put it
the elevator's a giant
elevator, yeah.
Put it
capacitor.
in a non-inertial reference frame.
Wow.
Moving at 0.9.
Put an accelerating reference frame.
Yeah, you guys-
The elevator's on a ramp, and the
I don't know if I'm gonna put,
We're going into
I may
general
keep this one.
relativity now.
This one's pretty good though. I should keep this one. All this information, yeah, I'll keep this. But for those of you that aren't in my class, for the very few of you that will watch this, you got kids obviously in our APC class where we did some crazy ramp stuff. And then our advanced physics class is doing special relativity. That's why there's insanity going. Okay, so let's do this. We have our capacitance of C. This is D, and this is A. We're all good, yes?
Yes.
That's our initial, yeah, C equals C. We good with that?
C.
Then I do this.
Oh, that's
Oh,
crazy.
snap.
So is that A over 4? You just do each.
Hold on. So let's talk about this one right here. By halving it, it's, so by making it smaller, you decrease the capacitance, right? By halving A would make it half as much capacitance, right?
Yes.
But then by shortening the distance would make it
Twice.
twice as much. So you're halving A and you're halving D, which equals,
C.
this is just C.
C.
Mi amigos.
So this one right here must be
KC.
kappa C. Kappa 2 times C.
KC.
And this one must be, remember you halved it, right?
Yeah.
So it's going to be C over 2 times kappa 1, not K1, kappa 1. Are we all good with that? And here's what I would do. So, first of all, these two are in series, right?
Yes.
So 1 over C left total will equal 1 over C plus 1 over kappa 2C, which would equal kappa 2C
Kappa 2 plus 1.
plus 1 over kappa 2C, right? So C left total
Or just-
equals
Wait.
kappa 2, did I do that right?
Just kappa
Kappa
2.
There's no
C in the
No C on
numerator.
top.
Yeah, I don't know why I do that. Sorry.
Hmm.
Then you have
Oh,
those two.
shoot, I gotta flip it, right?
C.
I think that's what happened.
Yeah.
You're trying to flip it.
Kappa 2C over. Yeah.
I just say that all the time.
Plus 1.
Yeah, we know.
Okay, so this is the left side, and we already know the right side, and because they're in series, they're in parallel, we just
Add them.
add them up. So C equivalent total equals
When would this ever happen?
AP, what are you thinking about? AP board, man.
Dude,
They would do this to us?
they're gonna give you
Why
10
not?
of these exact problems.
Why?
Because it's advanced physics, this is not baby physics.
This is advanced placement physics, not advanced physics.
And there's our total capacity.
Are you in?
Advanced.
And again, all we did was we found the individual capacitances, then we did these two in series, and then that with this one in parallel. We good?
Yeah.
Yo.
All right, go ahead and stop that.
Physics, Jack?